Hello everyone, I'm Prakhyath Jain, Assistant Professor, Department of Mechanical Engineering, AJIET Mangalore. Today I'm going to discuss about Module 3 of Fluid Mechanics, that is Class 3, continued portion of Fluid Dynamics. So let us discuss some problems related to head loss and Venturimeter and its related problems in this video today. So first problem, a pump has tapering pipe running full of water. The pipe is placed vertically with the diameters at the base and top being 1.2 meter and 0.6 meter respectively. The pressure at the upper end is 240 mm of Hg vacuum, while the pressure at lower end is 15 kN per meter square. Assume head loss to be 20% of difference of velocity head. Calculate the discharge. The flow is vertically upwards and difference of elevation is 3.9 meter. So this problem is related to a pump which has tapering pipe. So pipe is placed vertically, so it is a vertical position pipe. So with the diameters at the base and topping 1.2 meter and 0.6 meter respectively. So lower end diameter is larger value, that is 1.2 meter, and upper end it has diameter 0.6 meter. So consider section 1.1 at the lower end and section 2.2 at the upper end. So the pressure at upper end is 240 mm of Hg vacuum. So it is given, the pressure value is not given in terms of Newton per meter square or Newton per centimeter square. It is given in terms of head of mercury. That is the pressure head P2 divided by rho mg. There is a mercury head, so that is equal to 240 mm of mercury, that is a vacuum pressure. So P2 divided by rho mg, that is equal to vacuum pressure. So you have to consider negative sign here, minus 0.24. 240 mm has to be converted from millimeter to meter, that is 0.24, and negative sign, that is minus 0.24, because this is a vacuum pressure. The pressure below atmospheric pressure, that is a negative pressure, you have to consider minus here. So P2 divided by rho mg equal to minus 0.24. Now in order to get P2, you have to just multiply rho m into g to 0.24, that is minus 0.24. What is rho m? Rho m is density of mercury and g is acceleration due to gravity. Its value is 9.81 meter per second square. Then the pressure at lower end is 15 kilonewton per meter square, that is P1 equal to, because section 1.1 I consider at lower end, so P1 equal to 15 kilonewton per meter square. Assume head loss to be 20% of difference of velocity head. So HL equal to 20% of difference of velocity head. Velocity head is v square divided by 2g, so it is a difference. Let me discuss about that thing in a upcoming slide. So calculate the discharge, that is Q or rate of flow. The flow is vertically upwards. The flowing fluid, that is water, is flowing from lower section to upper section, and difference of elevation is 3.9 meter. So that is Z2 minus Z1, that is equal to 3.9. But assume Z1, that is a section 1.1, that is passing through the datum, so that Z1 equal to 0. So Z2 minus 0 equal to 3.9. So Z2 becomes 3.9 meter. So given D1 equal to 1.2 meter, D2 equal to 0.6 meter, P2 divided by rho mg equal to 240 mm of Hg vacuum. So P1 equal to 15 kilonewton per meter square, HL equal to 20% of difference of velocity head. So Z2 minus Z1 equal to 3.9 meter, P2 divided by rho mg equal to minus 0.24. So millimeter is converted to meter here, and negative sign you have to multiply because it's a vacuum pressure. So P2 equal to minus 0.24 into rho mg. So that is equal to minus 0.24 into 13,600 into 9.81. So that is equal to minus 32,019.8 Newton per meter square. There is a pressure at section 2.2. So as rho m equal to density of mercury, that is equal to 13,600 kg per meter cube. Or you can obtain density of mercury by using specific gravity. Specific gravity of mercury is 13.6, and specific gravity is defined as density of given fluid to density of standard fluid. Standard fluid is here water, so specific gravity is 13.6. 13.6 into 1000, that becomes 13,600 kg per meter cube. There is a density of mercury, or you can just remember density of mercury as 13,600 kg per meter cube. Then P1 equal to 15 kilonewton per meter square. I have to convert from kilo to Newton per meter square. Kilo is 10 to the power 3. So 15 into 10 to the power 3 Newton per meter square. Because you have to substitute pressure value, whatever the unit like bar, megapascal, you have to convert from that unit to Newton per meter square. So A1, if we know D1 and D2 values, so you can just calculate cross-sectional area. A1 equal to pi by 4 D1 square. So that is equal to pi by 4 into 1.2 square. That is equal to 1.1309 meter square. A2 equal to pi by 4 D2 square. So that is equal to pi by 4 into 0.6 square. So that is equal to 0.2827 meter square. So those are the cross-sectional areas A1 and A2. So using continuity equation, A1 V1 equal to A2 V2. So A1 value is 1.1309, A2 is 0.2827. So we can just use continuity equation to get relationship between V1 and V2, as V1 and V2 value are not given in problem. So 1.1309 V1 equal to 0.2827 V2. So we can get expression for V2 in terms of V1 as V2 equal to 1.1309 divided by 0.2827 V1. So that is equal to 4 V1. So V2 equal to 4 V1. But HL, that is head loss, is given as 20% of difference of velocity head. So among V2 and V1, it is given as difference. Higher value should be considered first. So V2 is higher. So V2 square minus V1 square divided by 2g, that is the difference of velocity head. Velocity head is V square divided by 2g. So it is given difference of velocity head. Higher velocity head minus lower velocity head. V2 square divided by 2g minus V1 square divided by 2g. Denominator is same, so you can combine together V2 square minus V1 square divided by 2g into 20%, that is 20 divided by 100. So HL equal to 0.2 into, in place of V2 we can substitute 4V1. So 0.2 into 4V1 whole square minus V1 square divided by 2 into 9.81. So that is equal to 0.2 into 15V1 square divided by 2 into 9.81. So that is equal to 3V1 square divided by 2 into 9.81. So that's the HL value in terms of V1. So applying Bernoulli's equation at section 1 and section 2, we get P1 divided by rho g plus Z1 plus V1 square divided by 2g equal to P2 divided by rho g plus Z2 plus V2 square divided by 2g plus HL, where HL is head loss. Now P1 value is 15 into 10 to the power 3 and P2 value is minus 32,019.8 and HL expression is known. We can just substitute. So we get 15 into 10 to the power 3 divided by 1000 into 9.81 plus Z1 plus V1 square divided by 2 into 9.81 is equal to minus 32,019.8 divided by 1000 into 9.81 plus Z2 plus V2 square divided by 2 into 9.81 plus HL. So we can rearrange the terms. So minus 32,019.8 divided by 1000 into 9.81, that becomes positive when it comes to left hand side. So 15 into 10 to the power 3 divided by 1000 into 9.81 plus 32,019.8 divided by 1000 into 9.81, take Z2 to other side, Z2 minus Z1 plus V2 square divided by 2 into 9.81 as it is minus V1 square divided by 2 into 9.81, taking V1 square divided by 2 into 9.81 to other side, so it becomes negative, plus 3V1 square divided by 2 into 9.81. That's a 3V1 square divided by 2 into 9.81 is a value of HL. So now we can simplify the expression. So 15 into 10 to the power 3 divided by 1000 into 9.81 plus 32,019.8 divided by 1000 into 9.1, that's its value is 4.7930 is equal to Z2 minus Z1. There's a difference of elevation, that is 3.9 plus V2 square. In place of V2 we can substitute 4V1 because we already got expression for V2 as 4V1. So 4V1 whole square divided by 2 into 9.81 minus V1 square divided by 2 into 9.81 plus 3V1 square divided by 2 into 9.81. So 4.7930 minus 3.9, that is 0.8930 is equal to 16V1 square, that is 4V1 whole square becomes 16V1 square divided by 2 into 9.81 minus V1 square divided by 2 into 9.81 plus 3V1 square divided by 2 into 9.81 is equal to, so 16 plus 3, that is 19, minus 1, that is 18V1 square divided by 2 into 9.81. So 18V1 square divided by 2 into 9.81 is equal to 0.8930, or we want expression for V1 or value of V1. So V1 square equal to 0.8930 into 2 into 9.81 divided by 18. So its value is 0.97337. So V1 square equal to 0.97337, or taking square root, V1 equal to 0.9865 meter per second. There's a velocity at section 1. Therefore, we can calculate the discharge. They have asked discharge. So discharge equal to A1 V1 equal to A2 V2. But we have values of A1 and V1. So we can just, I'll go with the first expression, Q equal to A1 V1. So Q equal to A1 V1 equal to, A1 value is 1.1309. V1 we got it as 0.9865. So just substitute. Q equal to A1 V1 equal to 1.1309 into 0.9865. So that is equal to 1.1156 meter cube per second. There's a value of rate of discharge. There's a first problem. So let's go for second problem. So a pipeline carrying oil of specific gravity 0.87 changes in diameter from 200 mm diameter at a position A to 500 mm diameter at position B, which is 4 meters at a higher level. If the pressures at A and B are 9.81 Newton per centimeter square and 5.886 Newton per centimeter square respectively, the discharge is 200 liter per second. Determine the loss of head and direction of flow. So I have to find loss of head and direction of flow here, whether the fluid is flowing from lower section to upper section or upper section to lower section. So I have to determine and I have to calculate loss of head, that is HL. So pipeline carrying oil of specific gravity 0.87 is given. Specific gravity is 0.87. So again, specific gravity equal to density of standard fluid, density of given fluid to density of standard fluid. So density of given fluid is you're supposed to find, that is of specific gravity 0.87 into density of standard fluid. So that is 1000, that's water. 0.87 into 1000, so 870 kg per meter cube. Changes in diameter from 200 mm diameter at position A to 500 mm diameter at position B. So it is a tapered pipe again. So 200 mm diameter at position A, there is a smaller value, or that is 200 mm equal to 0.2 meter, to 500 mm diameter at position B. So larger value, 0.5 meter. So dA equal to 200 mm, dB equal to 500 mm. So B, which is 4 meters at a higher level. So assume the datum, the point A is passing through the datum, so that ZA equal to 0 and ZB equal to 4 meter. If the pressure at A and B are 9.81 Newton per centimeter square and 5.886 Newton per centimeter square respectively, PA equal to 9.81 Newton per centimeter square and PB equal to 5.886 Newton per centimeter square, and the discharge is 200 liter per second. So Q value or rate of flow, it is given as 200 liter per second. Determine the loss of head and direction of flow. So first draw the diagram. So it is a tapered pipe, keep in inclined positions in such a way that point A that passes through that datum line and point B at a distance or height of 4 meter from datum line, and just write down the given data, that is pressure and diameter values. So is the diagram you are supposed to draw here. This mark for that diagram. So given things, Q equal to 200 liter per second. Liter per second should be converted to meter cube per second. That can be done by multiplying 10 to the power minus 3. So 200 into 10 to the power minus 3 meter cube per second, or that is equal to 0.2 meter cube per second. Specific gravity of oil, as I already told, it is given as 0.87. So density for oil, that is equal to 0.87 into density of standard fluid. So 0.87 into 1000. So that is equal to 870 kg per meter cube. At section A, dA equal to 200 mm. So convert from mm to meter, 0.2 meter. Then calculate the cross-sectional area. AA equal to pi by 4 dA square. So dA value is 0.2, pi into 0.2 square divided by 4. So that is equal to 0.0314 meter square. Then PA value, the pressure at section A or point A, it is given as 9.81 Newton per centimeter square. Convert from Newton per centimeter square to Newton per meter square. So 9.81 into 10 to the power 4 Newton per meter square. If datum is passing through A, then ZA equal to 0. So you have to draw the diagram in such a way that the point A is passing through datum. So that ZA equal to 0 and ZB equal to 4. So now continuity equation we know Q equal to AA into VA, that is equal to AB into VB. Now first let's go with first expression, that is Q equal to VA into AA. So VA value we can calculate because Q value and AA value is known. So VA equal to Q divided by AA. So VA value is 0.2, Q value is 0.2 divided by AA value is 0.0314. So VA equal to 0.2 divided by 0.0314. So that is equal to 6.369 meter per second. There is a value of velocity at section A. So at section B, dB equal to 500 mm. So that is equal to 0.5 meter. Convert from millimeter to meter. AB equal to cross-sectional area pi by 4 dB square. So that is equal to pi into 0.5 square divided by 4. So that is equal to 0.1963 meter square. Now pressure at point B, it is given as 5.886 Newton per centimeter square. Centimeter is 10 to the power minus 2 meter. So it is whole square, centimeter square. 10 to the power minus 2 meter whole square. So when it goes to numerator, it becomes 10 to the power 4 Newton per meter square. So 5.886 into 10 to the power 4 Newton per meter square. ZB value, that is equal to 4 meter. And again using continuity equation or equation for discharge, that is Q equal to AB into VB. So AB value is 0.1963, Q value it is given as 0.2. So just calculate VB. VB equal to Q divided by AB. So that is equal to 0.2 divided by 0.1963. So it is equal to 1.018 meter per second. There is a velocity at point B. So now total energy, they are asked direction of flow and loss of head. So total energy, it is a summation of pressure energy, then kinetic energy and potential energy. So that is pressure energy is P by rho g, kinetic energy is V squared divided by 2g, and potential energy is Z. So it is a summation of P divided by rho g plus V squared divided by 2g plus Z. Now for applying this equation for point A or section A, total energy at A, that is represented by EA, energy at A, that is equal to PA divided by rho g plus ZA plus VA squared divided by 2g. So PA value, ZA value and VA value we know. So we can just substitute. So that is equal to EA equal to 9.81 into 10 to the power 4 divided by 870 into 9.81. ZA value, as the point A is passing through datum, so ZA value equal to 0. So plus 0 plus 6.369 square divided by 2 into 9.81. So that is equal to 13.557 meter. So that is the energy at A. So next, total energy at B, that is represented by EB. Just replace PA by PB and ZB by ZA by ZB and VA by VB. So just write the expression EB equal to PB divided by rho g plus ZB plus VB square divided by 2g. So we know values of PB, ZB and VB. We can just substitute. So that is EB equal to 5.886 into 10 to the power 4 divided by 870 into 9.81. So rho value I have to take care here. It is of density of flowing fluid. Density of flowing fluid here is oil of specific gravity 0.87. So density becomes 870. So 5.886 into 10 to the power 4 divided by 870 into 9.81. ZB value is 4. So plus 4 plus 1.018 square divided by 2 into 9.81. So that is equal to 10.948 meter. So we obtain values of EA and EB. Now we can just compare which is higher. EA value is more than EB value. So always energy flows from higher value to or higher potential to lower potential. So higher value here is EA, so it is greater than EB value. So the flow of fluid is taking place from A to B. At right conclusion like that, first you have to calculate energy at points A and B. Then depending on the value, you have to determine the direction of flow, that is from higher to lower value. So flow is taking place from A to B. Now loss of head, that is just difference between two energy values. So that is EA minus EB, higher value minus lower value. So that is equal to 13.557 minus 10.948. So loss of head, it comes to be 2.609 meter. So this is a very important problem. So in examination point of view, so you just concentrate on this problem. So this is a second problem. Now let's go for fluid flow measurement. So what is fluid flow measurement? As the name itself indicates, it is related to measurement of flow. So it is a measurement of discharge or measurement of rate of flow. How much amount of fluid is flowing per second, because Q unit is meter cube per second. Meter cube is unit of volume. So how much amount of volume of water or any fluid that is flowing per second, that is called as discharge. So in order to measure that discharge, we should have some devices. So those devices are called as fluid flow measurement devices. So fluid flow measurement means the measuring the rate of flow of a fluid flowing through a pipe or through an open channel. So the rate of flow of fluid through a pipe is measured by Venturimeter, orifice meter, pitot tube, etc. Whereas through an open channel, the rate of flow is measured by notches and wires. So for a measurement of rate of flow through a pipe, we are going to use Venturimeter, orifice meter and pitot tube. Whereas for open channel, the notches and wires can be used. So this is the introduction part of fluid flow measurements. Let's go for application of Bernoulli's equation. So Bernoulli's equation application, or this Bernoulli's, first you have to know what is Bernoulli's equation. That is P by rho g plus Z plus V square divided by 2g, that is equal to constant. That is total energy remains constant. Or for two section points, P1 divided by rho g plus Z1 plus V1 square divided by 2g equal to P2 divided by rho g plus Z2 plus V2 square divided by 2g. That is for ideal case. If it is real, then you can just add plus HL to right hand side. So now let's first go for Venturimeter. What is Venturimeter? A Venturimeter is a device used for measuring rate of flow of a fluid flowing through a pipe. So is used for measurement of rate of flow or discharge through a pipe. So it consists of three important parts: a short converging part, a throat, and diverging part. It is based on principle of Bernoulli's equation. So Bernoulli's principle is total energy remains constant. So I'll discuss about converging part, throat, and diverging part in diagram. Next expression for discharge. Next slide. So Venturimeter, first you have to know what is Venturimeter. It's a device used for measurement of fluid flow through a pipe. So and it consists of three parts: converging part, throat, and diverging part. So next, the expression for rate of flow through Venturimeter. So consider a Venturimeter fitted in a horizontal pipe through which fluid is flowing, say water, as shown in figure. So you can see the diagram of Venturimeter here. So this Venturimeter we are going to fix to or fit to the pipe, horizontal pipe. There is a horizontal case here, horizontal pipe, to measure rate of flow. So pipe has diameter D1, or inlet of that Venturimeter is D1. And you can see there section 1 and section 2. Section 1, that is a converging part. So it is the area, diameter is gradually decreasing. So it is a converging part. And there is section 2, that is a throat of that Venturimeter. Then after that we have diverging part. So what is the principle of working of this Venturimeter? First you have to fit this Venturimeter to a pipe. Say in this case the water is flowing through a pipe, and you are going to fit this Venturimeter to a horizontal pipe. So principle of working is based on Bernoulli's principle, that is total energy remains constant. First let me start with section 1. So section 1, that is a converging part. As the here diameter is decreasing, that means the area is decreasing. So according to continuity equation, AV equal to constant, that is a product of area into velocity, that is equal to constant. So what is V? V equal to constant divided by A. Area decreasing means velocity is increasing. So velocity increasing means kinetic energy is increasing, because it is V square divided by 2g. Velocity increases means kinetic energy should increase. Now total energy, as per Bernoulli's principle, total energy should remain constant. So now as kinetic energy increases or velocity increases, there is a decrease in pressure to compensate for increase in velocity or kinetic energy. So this decrease in pressure can be measured by U-tube manometer. You can see there the section 1 that is and section 2 that is throat and inlet of the Venturimeter is connected to U-tube manometer. So that reduction in pressure can be measured by using U-tube manometer. Once you get reduction in pressure, you can obtain value of velocity. Once you get velocity, you can directly calculate discharge, that is Q equal to product of area into velocity. So that is the working principle. Total energy remains constant according to Bernoulli's principle. In converging section, area is decreasing. There is a tapered pipe or converging section. So because diameter is decreasing, so as a result the pressure is diameter is decreasing and area is decreasing. As a result, the velocity increases. Velocity increases means kinetic energy increases. So in order to compensate for increase in kinetic energy, there is a decrease in pressure. So that reduction in pressure or decrease in pressure is measured by U-tube manometer. So once you get a reduction in pressure, we can get value of velocity. By using value of velocity, we can calculate the discharge using expression Q equal to AV. So that's the principle of Venturimeter. So let's go for the derivation. So let D1 equal to diameter at inlet or at section 1, P1 equal to pressure at section 1 or inlet of the pipe, A1 equal to V1 equal to velocity of fluid at section 1, A1 equal to area of cross section. Once if we know the diameter, then we can directly calculate the area of cross section, that by using expression pi by 4 D1 square. And D2, P2, V2 and A2 are corresponding values at section 2. Now applying Bernoulli's equation at sections 1 and 2 we get. So we know the Bernoulli's equation. So for the ideal case it is, so P1 divided by rho g plus Z1 plus V1 square divided by 2g equal to P2 divided by rho g plus Z2 plus V2 square divided by 2g. As pipe is horizontal, the distance from center of the pipe to the datum, that is same. So Z2 minus Z1 or Z1 equal to Z2 equal to that is same value. So Z2 minus Z1, that becomes 0. So I can modify the expression as P1 divided by rho g plus V1 square divided by 2g equal to P2 divided by rho g plus V1 square divided by 2g, because Z1 minus Z2 or Z2 minus Z1, that is equal to 0. So now we can rearrange P1 minus P2 divided by rho g equal to V2 square divided by 2g minus V1 square divided by 2g. What is P1 minus P2 divided by rho g? There is a reduction in pressure. Reduction in pressure is measured by the U-tube manometer. So P1 minus P2 divided by rho g is H. There is a differential pressure head. So P1 minus P2 divided by rho g is the difference of pressure head at section 1 and 2, and it is equal to H, or P1 minus P2 divided by rho g equal to H. Now substituting this value of P1 minus P2 divided by rho g equal to H in the above equation, we get H equal to V2 square divided by 2g minus V1 square divided by 2g. Take it as expression 1. Now applying continuity equations at sections 1 and 2. So this continuity equation A1 V1 equal to A2 V2, or we can write expression for V1 or V2 here. I'll go with V1 here. So V1 equal to A2 V2 divided by A1. So we can substitute in place of V1 in expression 1 as A2 V2 divided by A1. So substituting this value of V1 in equation 1, so H equal to V2 square divided by 2g minus A2 V2 divided by A1 whole square divided by 2g. So you can take V2 square divided by 2g common. V2 square divided by 2g. What is the remaining term in first? So that is 1. 1 minus A2 square divided by A1 square. So that is equal to V2 square divided by 2g. Taking LCM, it becomes A1 square minus A2 square divided by A1 square. So that is H equal to V2 square divided by 2g into A1 square minus A2 square divided by A1 square. Now we can get expression for V2 by rearrangement, that is cross multiplying 2g to left hand side and dividing A1 square minus A2 square and multiplying A1 square. So H into 2gh divided by A1 square minus A2 square, and numerator it is multiplied by A1 square. So that is equal to V2 square. Now V2 square equal to 2gh into A1 square divided by A1 square minus A2 square. So we can get value of V2 by taking square root. V2 equal to square root of 2gh into A1 square divided by A1 square minus A2 square. Square root of 2gh, just split up the square root. So square root of 2gh into square root of a1 square, that becomes a1 divided by square root of a1 square minus a2 square. Now therefore discharge q, we got value of v2, we know a2, so we can calculate discharge q equal to a2 v2. So v2 value is square root of 2gh into a1 divided by square root of a1 square minus a2 square. So qth equal to a2 v2 equal to a2 into square root of 2gh into a1 divided by square root of a1 square minus a2 square. So that is equal to, upon rearrangement, a1 a2 into square root of 2gh divided by square root of a1 square minus a2 square. Take it as expression 2. So equation 2 gives the discharge under ideal condition, and it is called theoretical discharge. So this is a theoretical discharge and under ideal condition, that in that case the loss of head is equal to 0. Ideal condition means viscosity is not there. Viscosity is not there means friction is not there. Friction is not there means there is no loss. So that above expression 2, it is under ideal condition. Now we have to get expression for actual condition. So actual discharge will be less than theoretical discharge. So q actual equal to cd into a1 a2 square root of 2gh divided by square root of a1 square minus a2 square. Take it as expression 3. Now what is cd? cd equal to coefficient of Venturimeter, and its value is less than 1. In when the loss of head, that is equal to 0, in that case the value of cd is equal to 1. Then it becomes q theoretical. Q actual equal to q theoretical. So in order to get q actual, we have to just multiply cd, that's coefficient of discharge, for q theoretical, that's a theoretical discharge. So equation 3 by 2 gives cd equal to q actual divided by q theoretical. So we can define now coefficient of discharge as, coefficient of discharge is defined as ratio of actual discharge to theoretical discharge, that is q actual divided by q theoretical. Now one more expression is there for cd. You have to remember this expression as well. cd equal to square root of h minus hf divided by h. What is h? That is difference of pressure head. hf, as we all know, there is a loss of head due to friction. So h, square root of h minus hf divided by h. Under ideal condition, hf equal to 0. Then what is the value of cd? cd equal to square root of h minus 0 divided by h. Then cd equal to 1. So q actual equal to q theoretical, where hf is head loss due to friction in meter, and h equal to difference of pressure head in meter. So that's the terms h and hf. So coefficient of discharge, its value is less than 1. Only under ideal condition its value is equal to 1. Now value of h, that's the difference of pressure by differential U-tube manometer. There are 4 cases. Let's discuss one by one. So case 1, let the differential manometer contains a liquid which is heavier than liquid flowing through pipe. That is, manometric fluid has specific gravity greater than the flowing fluid. So then let SH equal to specific gravity of heavier fluid or manometric fluid, SO equal to specific gravity of liquid flowing through pipe, that is the specific gravity of flowing fluid. So x equal to difference of heavier liquid column in U-tube, then h equal to x into SH divided by SO minus S1. So difference of pressure head can be obtained by using expression h equal to x into SH divided by SO minus 1. What is x there? Difference of heavier liquid column in U-tube. So you can obtain the pressure difference by using this expression. Take it as expression 4. This is the case when manometric fluid has specific gravity greater than the flowing fluid. So then you can use this expression. Next, second case, if the differential manometer contains liquid which is lighter than the liquid flowing through pipe, then the value of h, this is exactly reverse of case of 1. So here in case 2, the manometric fluid has specific gravity lower than the specific gravity of flowing fluid. Then value of h, that's the difference of pressure head, that can be obtained as h equal to x into 1 minus SL divided by SO. What is SL? SL equal to specific gravity of lighter liquid in U-tube, and SO as it is, that is specific gravity of fluid flowing through pipe. So first case and second case. First case where specific gravity of manometric fluid or fluid in U-tube, that is greater than the flowing fluid. Second case, it is exactly reverse. Specific gravity of manometric fluid is lower than specific gravity of flowing fluid. Now case 3 and case 4. So case 3, inclined Venturimeter with differential U-tube manometer. The above two cases are given for horizontal Venturimeter. This case is related to inclined Venturimeter. So having a differential U-tube manometer, let the differential manometer contains heavier liquid than H is given as. So this is third case is related to inclined Venturimeter having differential U-tube manometer. So specific gravity of manometric fluid is greater than specific gravity of flowing fluid. So H equal to P1 divided by rho g plus Z1 minus P2 divided by rho g plus Z2 equal to X into SH divided by SO minus 1. X into SH divided by SO minus 1, that is same as case 1, but in case 1, H equal to P1 divided by rho g minus P2 divided by rho g. What about Z1 and Z2 values? Z1 and Z2 value, those are equal because is a horizontal Venturimeter. So Z1 equal to Z2, Z1 minus Z2 or Z2 minus Z1, that becomes 0. So here Z1 and Z2 values have finite value. So like Z2 is at higher level or Z1 is at higher level. So Z2 minus Z1, it is not equal to 0. So I have to consider Z1 and Z2 here. So H equal to P1 divided by rho g plus Z1 minus P2 divided by rho g plus Z2 equal to X into SH divided by SO minus 1. So this is a case of inclined Venturimeter with differential U-tube manometer having specific gravity greater than the flow of flowing fluid. So case 4, similarly for inclined Venturimeter in which differential manometer contains a liquid which is lighter than the liquid flowing through pipe, then the value of H is given as. So here specific gravity of manometric fluid is lighter than or it is lower than the specific gravity of flowing fluid. Then it is again same as case 2, but it is inclined Venturimeter. So I have to consider Z1 and Z2. So H equal to P1 divided by rho g plus Z1 minus P2 divided by rho g plus Z2, that is equal to X into 1 minus SL divided by SO. What is SL? SL is specific gravity of lighter liquid and SO is specific gravity of flowing liquid or flowing fluid. So these are the 4 cases you have to remember. For first and second case, H equal to P1 divided by rho g minus P2 divided by rho g. I have not mentioned that expression in this slide. You have to just remember, you have to use that expression for solving the problem. P1 divided by rho g minus P2 divided by rho g, that is equal to H, that is equal to X into SH divided by SO minus 1, that is for case 1, and case 2, H equal to P1 divided by rho g minus P2 divided by rho g equal to X into 1 minus SL divided by SO, that is for case 2. Then case 3 and case 4, I have mentioned the expressions. You can just remember those expressions. So first case 1 and case 2 for horizontal Venturimeter, case 3 and case 4 for inclined Venturimeter. Let's go for problem. First problem, horizontal Venturimeter with inlet and throat diameters at 30 cm and 15 cm respectively is used to measure the flow of water. The reading of differential manometer connected to inlet and throat is 20 cm of mercury. Determine the rate of flow. Take CD equal to 0.98. So CD, that is coefficient of discharge, they have told to take value of CD as 0.98. So this is a case of Venturimeter, horizontal Venturimeter with inlet and throat diameter. So inlet diameter of the pipe or inlet diameter of the Venturimeter, that is same, one and the same. So D1 equal to 30 cm, D2 equal to 15 cm, that is throat diameter, is used to measure the flow of water or rate of discharge. The reading of differential manometer connected to inlet and throat is 20 cm of mercury. So this is very important. This is not H. The H means is the difference of pressure head. Here it is the X value is elevation of the manometric fluid in U-tube. So that is X value. In terms of mercury, it is given 20 cm of mercury. So you should be careful. X and H value. H is difference of pressure. X is the elevation or height increase or height in manometer. So determine the rate of flow, that is Q. Now specific gravity of flowing fluid. What is flowing fluid here? That is water. What is the specific gravity of water? Specific gravity of water is 1. That is a standard fluid. So specific gravity of water is taken as 1. Then specific gravity of mercury, that is SH, that is equal to 13.6. That's the specific gravity. Then reading of differential manometer, x equal to 20 centimeter. From centimeter to convert to meter, so 20 divided by 100, that is equal to 0.2 meter. Therefore, difference of pressure head, it is the case 1, because specific gravity of manometric fluid is greater than specific gravity of flowing fluid. 13.6 is greater than 1, so you can consider case 1, and it is a horizontal Venturimeter. So difference of pressure head H equal to x into SH divided by SO minus 1. So x value is 0.2, SH is 13.6, SO is 1. So 0.2 into 13.6 divided by 1 minus 1 equal to 2.52 meter of flowing fluid. What is a flowing fluid here? That is water. So 2.52 meter of water. So diameter at inlet or pipe diameter D1 equal to 30 centimeter. Convert from centimeter to meter. So that is equal to 0.3 meter. So D1 equal to 0.3 meter. Now once diameter is known, you can calculate cross-sectional area, that is A1. A1 equal to pi by 4 D1 square. So A1 equal to pi by 4 D1 square. So that is equal to pi into 0.3 square divided by 4, as D1 value is 0.3. So that is equal to 0.07068 meter square. Then D2 value, that is a rod diameter. So that is equal to 15 centimeter. Convert from centimeter to meter, 15 divided by 100, so that is equal to 0.15 meter. Then A2, you can calculate cross-sectional area, A2 equal to pi by 4 D2 square, so that is equal to pi into 0.15 square divided by 4, so that is equal to 0.01767 meter square. CD value, that is coefficient of discharge, it is given as 0.98. So expression for coefficient of discharge for horizontal Venturimeter, the discharge Q is given by Q equal to CD into A1 A2 square root of 2GH divided by square root of A1 square minus A2 square. A1 and A2, those are cross-sectional areas at section 1 and section 2, and H is difference of pressure head, and CD is coefficient of discharge, and Q is rate of discharge. So we can substitute the values. Q equal to CD value is 0.98, so 0.98 into A1 value is 0.07068, A2 is 0.01767, and H is 2.52. So 0.98 into 0.07068 into 0.01767 into square root of 2 into 9.81 into 2.52 divided by square root of 0.07068 square minus 0.01767 square. So upon simplification, 0.125756 meter cube per second. So if you have confusion in writing the unit, just check with the expression Q equal to AV. Unit of A is meter square, V has unit meter per second. Meter square into meter, that becomes meter cube divided by second, so meter cube per second. Because we are substituting all the values in SI unit, there's a meter, so we are going to get the value of Q in meter cube per second. So now meter cube per second you can keep as it is, otherwise you can convert to liter per second. In some of the questions they're going to ask like find out the discharge in liter per second, so it's better to know. So how to convert from liter to meter cube? To convert, we multiply 10 to the power minus 3. It is exactly reverse, meter cube per second to liter per second. There you multiplied by 10 to the power minus 3, here you divide by 10 to the power minus 3. So when 10 to the power minus 3 goes to numerator, it becomes 10 to the power plus 3. So 0.125756 into 10 to the power 3. So that is equal to 125.756 liter per second. There is a value of discharge. Second problem, an oil of specific gravity 0.8 is flowing through a Venturimeter having inlet diameter 20 cm and throat diameter 10 cm. The oil mercury differential manometer shows a reading of 25 cm. Calculate the discharge of oil through horizontal Venturimeter. Take CD equal to 0.98. Again, this is the case of horizontal Venturimeter and oil of specific gravity 0.8. So oil of specific gravity 0.8 is flowing. There is a flowing fluid is oil of specific gravity of 0.8. The inlet diameter, that is D1, that is equal to 20 cm. Throat diameter, that is D2, equal to 10 cm. The oil mercury differential manometer shows a reading of 25 cm. Again it is X not H. X equal to 25 cm. Calculate the discharge of oil through horizontal venturimeter. Q equal to how much? Take CD equal to 0.98. This coefficient of discharge, that is equal to 0.98. Let's go for solution. Specific gravity of oil, that is SO, a flowing fluid, that is equal to 0.8. Specific gravity of mercury, that is SH, heavy liquid, that is equal to 13.6. So it's a case of first horizontal venturimeter with specific gravity of manometric fluid greater than specific gravity of flowing fluid. That's a case 1. So reading of differential manometer, it is given as x equal to 25 centimeter, convert from centimeter to meter. 25 by 100, that is equal to 0.25 meter. Then difference of pressure head from case 1, H equal to P1 divided by rho g minus P2 divided by rho g, that is equal to x into SH divided by SO minus 1. So P1 divided by rho g minus P2 divided by rho g is of no use here. You can just ignore that expression. So you can go with H equal to x into SH divided by SO minus 1. So SH value is 13.6, SO value is 0.8. And x value it is given as 25 centimeter. So convert from 20 centimeter to meter, that is 0.25 meter. So 0.25 into 13.6 divided by 0.8 minus 1. So that is equal to 4 meter of working fluid or flowing fluid. What is the flowing fluid here? Flowing fluid is oil. So 4 meter of oil. While writing unit, you should be careful. It should be written in terms of head of flowing fluid. So 4 meter of oil. In previous problem, it was 4 meter of water because flowing fluid was water. Here it is oil of specific gravity 0.8. So I have to write in terms of oil. So 4 meter of oil. Now diameter at inlet, that is D1 equal to 20 centimeter. So convert from centimeter to meter, 20 divided by 100. So that is equal to 0.2 meter. Then cross-sectional area A1 equal to pi by 4 D1 square. Now D1 value is 0.2. So we can easily calculate A1. So A1 equal to pi by 4 D1 square. So pi by 4 into D1 is 0.2 square. So that its value, that's the area of cross section at section 1, A1 equal to 0.0311416 meter square. So D2 equal to, this is the rod diameter, it is given as 10 centimeter, convert from centimeter to meter, 10 divided by 100, so that is equal to 0.1 meter. So cross sectional area at section 2 or rod A2 equal to pi by 4 D2 square. So D2 value is 0.1, so pi into 0.1 square divided by 4. So that is equal to, A2 value is equal to 0.007854 meter square. So this is a value of A2. Now once you get, we get value of A1 and A2, CD value it is given in quotient, that is coefficient of discharge, that is equal to 0.98. Then discharge Q is given by, for horizontal venturimeter, Q theoretic, Q actual is actual case because CD is given. Q equal to CD into A1 A2 square root of 2GH divided by square root of A1 square minus A2 square, where A1 A2 those are cross sectional areas at inlet and throat, and H is difference of pressure head, and CD is coefficient of discharge, Q is rate of flow or discharge. So Q equal to 0.98 into area A1 is 0.031416 and A2 is 0.007854 and H value is 4 meter of oil. Just substitute Q equal to 0.98 into 0.0311416 into 0.007854 into square root of 2 into 9.81 into 4 divided by square root of 0.0311416 square minus 0.007854 square. So upon simplification, we get value of Q as 0.070465 meter cube per second. Again, if you have confusion with respect to unit, just remember Q equal to AV. Unit of A is meter square, unit of velocity is meter per second. So overall unit becomes meter cube per second. So it is not heat, it is discharge. So meter cube per second, 0.070465 meter cube per second. So like as I told in previous problem also, in some of the problems they are going to ask find out the discharge in liter per second. So 1 liter is 10 to the power minus 3 meter cube. So now in order to get meter cube per second, to convert meter cube per second to liter per second, I have to just divide by 10 to the power minus 3. 10 to the power minus 3 when goes to numerator, it becomes 10 to the power 3. So 0.070465 into 10 to the power 3. So what is the value? 70.465 liter per second. Otherwise you can keep in meter cube per second if they are not going to specify, like calculate discharge in liter per second, then you can calculate the discharge in SI unit, that is meter cube per second. If they ask to get the discharge in liter per second, then just multiply 10 to the power 3 or divide by 10 to the power minus 3, and 10 to the power minus 3 it goes to numerator, it becomes 10 to the power 3. So 0.070465 into 10 to the power 3, that becomes 70.465 liter per second. So in this video I discussed about the loss of head problem, let's say for Bernoulli's equation for real fluid, and direction of flow of fluid, and the loss of head, and application of Bernoulli's equation, that is Venturimeter. So Bernoulli's principle you have to remember here, the total energy remains constant. In Venturimeter, because of the converging section, diameter is gradually decreasing. Diameter decreases means area is decreasing. So AV equal to constant. So velocity equal to constant by area. So area decreases means velocity increases. Velocity increases means kinetic energy increases, because kinetic energy equal to v square divided by 2g. To compensate for increase in kinetic energy, there is a decrease in pressure. So pressure reduction from inlet to throat. So that can be calculated by using or determined or measured by using U-tube manometer. So that gives a value of H. And like there are some cases 1, 2, 3, 4. So case 1 and case 2, that is related to horizontal Venturimeter, that is P1 divided by rho g minus P2 divided by rho g, that is equal to H equal to X into H divided by SO minus 1. If this is specific gravity of manometric fluid is greater than specific gravity of flowing fluid, then H equal to P1 divided by rho g minus P2 divided by rho g, that is equal to X into 1 minus SL divided by SO. If specific gravity of manometric fluid is lower than specific gravity of flowing fluid. Similarly, inclined cases with specific gravity greater than specific gravity of manometric fluid is greater than specific gravity of flowing fluid, that is H equal to P1 divided by rho g plus Z1. You have to consider Z1 here. Don't remember inclined Venturimeter, Z1 and Z2 values, that is not same. So there is a finite value for Z1 minus Z2. So you have to consider that thing. P1 divided by rho g plus Z1 minus P2 divided by P2 plus P2 divided by rho g plus Z2, that is equal to X into SH divided by SO minus 1. That is the case where specific gravity of manometric fluid is greater than specific gravity of working fluid. And last case, inclined Venturimeter having specific gravity of manometric fluid lower than specific gravity of working fluid or flowing fluid, that is P1 divided by H equal to P1 divided by rho g plus Z1 minus P2 divided by rho g plus Z2, that is equal to X into 1 minus SL divided by SO, where SL is specific gravity of manometric fluid or lighter fluid. You have to remember these 4 expressions, that will be very useful in solving the problems. So I solved today 2 problems related to horizontal Venturimeter considering CD value. So there is like alternate expression for CD, that is CD equal to square root of H minus HF divided by H. Using that I am going to solve some more problems in next video. So just remember the expression case 1, case 2, case 3, case 4, and an equation for discharge. So these are the this is the topic. Like in next slide I am going to discuss the inclined Venturimeter, and by using P1 divided by rho g plus Z1 minus P2 divided by rho g plus Z2, we are going to calculate the pressure difference. Okay, thank you.